Hello, my name is Declan Healy and I'm a test engineer for the CATV product line in MACOM Technology Solutions. Today I'm going to demonstrate one of our FTTx amplifier products and perform a measurement on the transimpedance gain from the optical input to the RF output of the amplifier. MACOM currently offers two FTTx amplifiers. These are the MAAM-010333 and the MAAM-008863. Further information can be found on our company website at www.macomtech.com. These FTTx amplifier products can be used to interface directly to an optical triplexer or photodiode application, providing a full integrated solution, eliminating the need for complex and expensive matching to the photodiode. The key parameters of these products are high transimpedance gain with tilt flexibility, low EIN and high linearity. And today I will demonstrate an effective method of performing a bench calibration and measurement on the amplifier.
Transimpedance gain of the FTTx amplifier is measured on a vector network analyzer, which is referred to as a VNA in the rest of this video. The VNA shown here is Agilent's 8753ES, which is a 75 ohm analyzer. The RF test cables used are 75 ohm type N to type F and can connect directly to the VNA ports, DUT and laser transmitter without the need for minimum loss pads. Minimum loss pads can be used on a 50 ohm analyzer, but because they are resistive, they will impact the measurement resolution of the reference photodiode current using the method shown later in this video. The VNA is first calibrated to the end of the RF test cables with a full 2-port SOLT calibration using Agilent's 85039B Type F calibration kit. After the calibration is completed, a 10 dB attenuator is connected to the laser transmitter's RF input. This is used to improve matching, but is not an absolute requirement for the setup. The VNA port 1 cable is then connected to this attenuator. Shown here are typical pictures of a clean and contaminated ferrule on single-mode fiber optic cable. Contamination of the ferrule will severely reduce the amount of optic power transferred from a fiber optic cable. The ferrule on a fiber patch cord is cleaned using a cassette cleaner. The fiber ferrule is rubbed off the exposed tape in one direction only, and it should not be rubbed off in the same area of the tape each time, as this could recontaminate the ferrule again. Care should be taken in reattaching the fiber cable to any adapters, so as to not recontaminate the fiber ferrule again. The fiber cable shown here has an FC connector, and it is being attached to an FC to SC adapter. The photodiode SC APC connector must also be cleaned. Do not assume that a fiber ferrule is clean even if you cleaned it before the previous connection. Even a new, unused fiber optic cable or photodiode pigtail should be cleaned before use. The ferrule can also be visually inspected for contamination using a fiber microscope, which has a very high magnification. The one shown here is a very basic model, but the objective is to inspect the end of the ferrule for contamination. Always ensure that the fiber is not live when looking at the ferrule. The transimpedance amplifier gain test setup requires a VNA, a 1550 nm laser transmitter, an optical attenuator, a DC power supply, and an ammeter. The reference photodiode PCB uses the same type of photodiode that is used on the DUT PCB. The photodiode anode is attached to the ground plane on the PCB, and the cathode is attached to the PCB track. The VNA port 2 RF cable is connected to the PCB-F connector, and the SC APC photodiode connector is attached to the fiber optic cable coming from the optical attenuator. The reference photodiode bias from the PSU is connected to the rear of the VNA so that the voltage will appear at port 2 of the VNA, eliminating the need for a bias T. This bias is also applied through the ammeter so that the photodiode current can be set to a specific value which is controlled by the optical power applied to the photodiode. If minimum loss pads were used with a 50 ohm VNA, there would be a voltage drop across the MLP and the ammeter would measure the current in the photodiode and MLP. The photodiode bias is plus 12 volts, and the optical attenuator is adjusted until the ammeter displays approximately 0.2 milliamps. The VNA reference level and scale per division are adjusted until the S21 data trace is shown on the display. This S21 data trace is then stored in the analyzer's display memory. The S21 data trace is then normalized with the memory data trace, thereby effectively setting the test setup loss to 0 for the purpose of the measurement. This is required so that the gain of the DUT can be measured accurately. The VNA reference level and scale per division are again adjusted until the S21 trace is shown on the display at 0 dB. After the reference photodiode measurement is done, then the PCB can be disconnected. This is done by first disabling the optical power and turning off the DC bias. The SC, APC connector and RF test cable are then disconnected. The leads from the PSU to the rear of the VNA are also removed, or else plus 12 volts will be present on port 2 of the VNA where the PSU is next turned on. The DUT PCB was connected to port 2 of the VNA. The photodiode on the DUT was cleaned and inspected with the fiber microscope. The photodiode SC APC connector was attached to the optical fiber cable coming from the optical attenuator. The DC bias was connected to the DUT PCB with a ribbon cable. The optical power and DC bias were then turned on. The ammeter was reconnected so that the current from the photodiode could again be measured. The optical power was adjusted slightly again until the ammeter measured approximately 0.2 milliamps. This adjustment was required as there was a slight difference in the responsivity of the reference and DUT photodiodes. The gain of the DUT will be accurate as long as the reference and DUT photodiode currents are set to the same value. The S21 trace on the VNA display now shows the gain of the TIA with uptilt. The device that was measured was a MACOM 010333.
Today I demonstrated an accurate measurement of measuring the transimpedance gain of the FTTx amplifier, thereby eliminating the need for the photodiode contribution to the measurement and providing the gain of the DUT only. Thank you for watching our video on testing MACOM FTTx amplifiers. For more information, visit our website at www.macomtech.com or contact one of the members of our application team.